Well, you think the El Nino and monsoon teleconnection story has been told already in so many papers, and what's left? As you know, during El Nino, the monsoon tends to be deficit, which means somewhere around 60% of the monsoon droughts are explained by El Nino, which means there are large fractions which are not necessarily associated with El Nino. And this correlation is typically based on the Nino 3 index of the El Nino being correlated with the all India monsoon rainfall, but people have also gone into details of how the correlations evolve seasonally, how they work at intra-seasonal timescales and not just at seasonal timescales. And there are papers arguing that the correlation between Nino 3 and all India monsoon actually became weaker after the regime shift of 1979 or so, and all these debates still keep going. And of course, there is the general understanding that when El Nino happens, there is a shift in the convection from the Western Pacific over the maritime continent, Western Pacific towards the east, and there are induced anomalous subsidences over other regions, especially over the Indian Ocean and the Indian monsoon region. I will just say in words what the paper is all about, and then you can decide whether you need to listen to the whole podcast. What they do here is go back to the daily rainfall from more than 100 years of all India monsoon rainfall record at quarter degree by quarter degree resolution, and they look at daily time scales to see within the overall reduced rainfall what is actually happening to extreme rainfall. It turns out that there are processes such as warm surface causing air to rise, and when it's near the surface it's rising, and the plume of rising air with moisture is not getting diluted, so it's called undiluted plume, and it bursts through the boundary layer into a moist atmosphere and is able to extract heavy rain. And this process is enhanced during El Nino years. So they compare El Ninos and La Ninas and normal years and show that in fact during El Nino, despite the overall reduction in mean rainfall, and there is also a trend now, and there is global warming which is moistening the atmosphere. Considering all those things, it turns out that El Nino actually has a clear signal in terms of increasing extreme rainfall over certain regions, not all of India. So the peninsular India and northwest India, which are typically drier, are not affected in this way. Core monsoon zone is affected, and the western Ghats, which are heavily influenced by the orographic effects, are also influenced by El Nino on the extreme rainfall. That's the summary, okay? More extreme monsoon rainfall in El Nino summers. Definitive statement. Extreme rainfall during the summer monsoon can be destructive and deadly to the world's third largest economy and most populous country. Although El Nino events in the equatorial Pacific are known to suppress total summer rainfall throughout India, we show the using observational data spanning 1901 to 2020, significantly long time series, that counterintuitively they simultaneously intensify extreme daily rainfall. So there is a seasonal time scale, intra-seasonal time scale, and daily rainfall. When rain does occur, it seems to rain heavily during an El Nino summer. This is partly driven by increases in extreme daily values of convective buoyancy, which allows the parcel to rise, and even if it expands and cools, it has condensation heating, which can keep it going through the boundary layer into the free atmosphere, which is moistened and can provide a lot of rain. So this happens provided that both the undilute instability of near surface air and the dilution by mixing with drier air above are considered. El Nino could plausibly drive similar changes in other tropical regions, and our framework could be further applied to changes in hourly extremes to other internal variability modes and to forced trends under climate change. So the future projections of extremes can be reconsidered in this framework as well. Internal variability modes are, of course, El Nino, La Nina. There are other zonal modes in the Indian Ocean and the Atlantic Ocean, as well as influences from the North Atlantic, Southern Ocean, and so on. But the opposite, so I'm going to jump ahead and read some of the text. There is some introduction given to how El Nino and monsoon correlations have been interpreted so far. But the opposite rainfall intensity signal emerges in the summer monsoons, climatological rainy areas, the broad central monsoon zone or the core monsoon zone in central India, and the narrow southwestern band between the Arabian Sea and the Western Ghats mountains of peninsular India. Within them it tends to rain less overall and less often during monsoon summers, but more intensely when the rain comes. So the rainy regions do see a reduced seasonal amount, but that amount is falling in a way that when it's raining more intensely, which obviously you measure in terms of percentiles. Whether these signals in rainfall intensity stem from destructive extreme daily rainfall events or agriculturally beneficial moderate rainfall days, and what their mechanistic origins are, remain unanswered, and this paper tries to answer it. Observational studies have investigated ENSO's influence on daily or hourly rainfall extremes in other tropical domains, but not in the Indian summer monsoon. So much more of a subtle analysis to extract additional insights. People have looked at how El Nino and La Nina affect active and break periods, how global warming is projecting into active monsoon periods, and I always argue that this is one of the most intrinsic time scales. Of course, there's diurnal cycle as well. And so influences on extreme daily rainfall. Then jumping ahead, we'll see a figure in a minute. Few figures in a minute. Our primary metric of extreme daily rainfall is the cutoff accumulation computed as the ratio of the variance to the mean of daily rainfall across summer days. So you have daily mean and then you have rainfall variance within the day. So they look at the ratio. This metric is motivated by the reliably gamma-like distribution of daily rainfall. Gamma distribution is obviously good for positive definite quantities like rainfall. You have zero or positive numbers, no negative numbers, and there are some details about how many parameters it takes to describe the distribution, etc. Probabilities follow a shallow power law below the cutoff before dropping off exponentially above it, as we'll see in a minute. Increasing the cutoff, which in the increasing the cutoff, which in the exact gamma limit is identical to the scale parameter, therefore makes all extreme rain rates more likely. So we'll look at some probability distributions as well. Our primary data set is the India Meteorological Department daily 0.25 by 0.25 gridded rainfall product spanning 1901 to 2020, derived from a dense, temporally varying in situ rain gauge network. So people have done processing consistently or to produce this more than a century-long product. We used all 122 days within each June, July, August, September summer monsoon, and all grid points within the monsoon India domain they call AMI. So we'll see that figure where the data set is most reliable. As shown below, key results are robust across alternative metrics of extreme and to another daily rainfall data set, 1 degree by 1 degree product. These signals in extremes differ qualitatively from those in less severe rain rates, which are suppressed throughout the domain by El Nino. This difference can be seen in ENSO risk ratios for each region, which are defined at each daily accumulation as the fraction of rainy days that accumulation value in El Nino summers divided by the corresponding fraction for La Nina summers. Okay, so daily accumulation each day as the fraction of, this is the El Nino risk, fraction of rainy days that accumulation value in El Nino summers divided by the corresponding fraction. So typically you contrast La Nina versus El Nino to see the extremes. La Nina goes one way, El Nino goes the other way. You can do this against normal years as well, but it's much nicer contrast this way. Okay, results don't change, hopefully. But for the other regions, the risk statistically significant reductions in the likelihoods of weak to moderate accumulations emerge in all 4 regions, and for Southeast India this reduction extends to the extremes as well. But for other regions the risk ratio minimizes at moderate accumulations, and then near the climatological cutoff, so we will see that they begin increasing quasi-exponentially with accumulation, the signature of an increased cutoff. Cutoff is basically again doing a percentile or a threshold, right? Accumulations exceeding 250 mm, for example, statistically significant increases in likelihood are 43%. So for accumulations exceeding 250 millimeters, statistically significant increases in likelihoods are 43% for the whole domain, 59% for the core monsoon zone or the central monsoon zone, owing to greater interannual variability in this quantity for the southwestern coastal band, the Ghats region. The 48% increase there is marginally statistically significant at 0.07 p. Presumably due to sampling uncertainty, behaviors for accumulations exceeding 300 mm are not statistically significant and are too erratic to be meaningfully physically interpreted. None of these key results are qualitatively sensitive to the let me read it again. I am hungry, dinner time. None of these key results are qualitatively sensitive to the specific methods or data set chosen. Okay, so we got the main gist of the study here, but we have to understand the mechanisms better. So we are looking at climatological June, July, August, September rainfall. This is the CMZ, core monsoon zone or central monsoon zone. These are the Western Ghats. This is the Southeast India peninsular region. This region basically gets northeast monsoon, not so much southwest monsoon, but is obviously seeing reduced rainfall and reduced extremes during El Niños. And these are the cutoff rain rate versus Nino 3.4, the ENSO index. Here it's rainfall millimeters per day. You can see maximum here and more here than here, for example. We are not worrying about this region. Correlation coefficients, obviously here you can see higher correlations here of cutoff rain rate versus Nino 3.4, and you see patchy and increased correlations here versus the SEI and the Northwest, which is not considered. And here we are looking at daily rain in millimeters. So you have less than 1 millimeter, so dry day in this gray band here, and this is the probability density in 1 over millimeter. So you have 0.25 by 25 degree, 0.25 by 0.25 degree product, and 1 degree by 1 degree product, just to say that data sets don't matter. And you are looking at the various rain rates and probability densities for the all India monsoon, so all grid points, core monsoon zone, Western Ghats, and the southeastern Indian region. Obviously, at low rain rates, you have lots of probabilities of rainfall, and as you increase the rain rates, you begin to drop off in the probability density, and you can see southeast India drops off much more sharply than the Western Ghats or the core monsoon zone. Here, core monsoon zone and the all India points are basically the same. Okay, you get the idea. I'm not going to read the detailed caption here, but positive values indicate that extreme rainfall is enhanced for El Nino compared with La Nina conditions. Okay, so that's the basic message. And then you look at more details. Light to moderate accumulation likelihoods are suppressed everywhere. So you're looking here at El Nino years, all years, and La Nina years, and region aggregated cutoff in millimeters versus region. And you can see again El Nino versus La Nina, different data sets and all India rainfall points, and the core monsoon zone, Western Ghats, and SEI. Western Ghats is higher for all of them, but La Nina and normal are lower in the region aggregated cutoffs, whereas El Nino surely jumps up over the Western Ghats and the core monsoon zone, which is the focus. And here over SCI, La Nina has got higher slightly than El Nino, so extremes also drop off here, not just the light ones. Okay, so that's the main story here, and there is another way to look at it: El Nino versus La Nina risk minus 100, so you see relative percentages, and you can see that as daily rain rates in millimeters go up, the SCI risk drops off, and there is errors when you go to very high rain rates, about 250 towards 300, as was mentioned in the text we read. But here you can see that over all these regions, the risk is going up in terms of percentages over the Western Ghats, core monsoon zone, and all monsoon grid points. Okay, so again, why is this happening? That's the main question. Let's look at one more figure before we go back to read. And this figure relates to that. Basically, they're going after the so-called buoyancy, convective buoyancy, BL, rainfall versus BL for all days. High ratio here, the correlation is very high over the Western Ghats and the core monsoon region, lower over the Southeast India and the Northwest, dry region, semi-arid and dry regions here. So you are looking at rain and the convective buoyancy, BL, meters per second squared. And as you go from negative buoyancy towards zero, you can see there are the PDFs of the BL, and you see the rain rates, BL PDF in 1/meter per second squared, and the rain. You can see that the rain suddenly jumps up as the BL reaches small negative numbers, which means you have the ability of the undilute air mass near the surface rising and pushing into the moist free atmosphere and extracting lots of rain. You can see these rain rates jump up very rapidly here, up to 100 millimeters, and obviously you are looking at events, daily time scale within sub-daily variance and so on, and obviously they are looking at accumulated cutoff rain rates, so you don't necessarily see 250 in the scale here, but when you accumulate they will show up. Okay, so here again this is AMI rain quantiles conditioned on BL, and again El Nino is basically not visible here because of the small changes, as they say, in this metric of all India monsoon rain quartiles conditioned on PL. But the message is that during El Nino, there is an overall subsidence and reduction in mean rainfall, but extremes can still jump out, because whenever, it's not like rain goes away during an El Nino. So whenever it rains, it has this process going on, which is extracting heavy rain, heavier during El Nino than La Nina. Okay, so that's the local convective buoyancy strongly controlling daily rainfall, and I won't read the caption again. So what are the mechanisms? Mechanism and so forth changes in convective buoyancy extremes. In general, one expects heavy rain where near surface air is especially warm and moist and is sitting below air that is nearly saturated. So that can be caused by, moistening is still happening because you have strong southwesterly winds and the back winds from the Bay of Bengal. There is also the discussion on low pressure systems and how they are interacting in this whole process, which are, a reasonable number per season. These conditions enable the near surface air to easily begin rising, precipitating out copious amounts of rainfall as it ascends, despite losing buoyancy to cooling through expansion and to dilution through mixing with the drier ambient air. These processes have been encapsulated into a scalar matrix of convective buoyancy known as BL, which we computed for each grid point and summer day of 1979 to 2020 using European Centre for Medium Range Weather Forecasts reanalysis ERA 5. Daily rainfall depends strongly, I'm jumping ahead, daily rainfall strongly depends on local convective buoyancy. The parcel has to start rising with nonlinear Spearman correlation coefficient positive at every grid point, as we saw here, up to 0.71, and expected quasi-threshold relationship in region aggregated conditional averages, as we saw here, and quantiles. So 3C was the quantiles of rainfall as a function of local buoyancy. So you're going down into a grid scale. Rainfall is so they typically aggregate and do composite daily rainfall at each grid point for each day of the season. Okay, otherwise you'll have too much noise in the data. Okay, rainfall that's some kind of a filtering, right? So rainfall is typically absent or weak until buoyancy reaches a threshold value slightly less than 0, above which rainfall increases sharply and rapidly, consuming buoyancy with it. So that's very obvious here. Buoyancy is increasing and then it crashes because it's converted into rainfall, which you can see ramps up super exponentially here. Okay, these conditional curves rise to higher rainfall values in the rainy southwestern coastal band and central monsoon zone compared with those for drier southeast India, but for a given region, to first approximation, they are insensitive to the state of ENSO. Okay, that's why ENSO line doesn't show up separately here except at very high rain rates here. Okay, the red line. This consistency of the rainfall buoyancy relationship across ENSO states, combined with the responses of the convective buoyancy distributions themselves to ENSO, help explain the responses of rainfall to ENSO. That's El Nino and La Nina. At the summer mean time scale, point-wise correlations of convective buoyancy against Nino 3.4 are negative at every grid point. It is shown in a supplemental figure. But for extremes such as the 99th percentile rainy day values, they are significantly positive over much of central eastern India, but significantly negative over much of the southeast and northwest, which are drier. These signals are shared by the individual buoyancy components, which we looked at. Oops, that's did I strip it out? What did I do with figure 4? Yeah, sorry. Let me bring in figure 4. Somehow I forgot to include it, so I'm going to pause it and come back. Okay, so sorry about that. This happens because I do these things when I have time. This is just something I do voluntarily for fun. I enjoy doing these, so sometimes I'm tired, I'm not as careful as I should be, etc. Without making any more excuses, we will see that both, let me bring up, but for extremes such as the 99th percentile rainy day values, they are significantly positive, these correlations between BL and Nino 3.4 over central eastern India, but significantly negative over much of the southeast and northwest. These signals are shared by the individual buoyancy components, both nearly saturated and very gravitationally unstable days near the orography are predominantly enhanced over eastern central India versus suppressed over the northwest and southeast. Okay, so here we are, figure 4, right tail daily convective buoyancy occurrence under ENSO largely tracks with the extreme rainfall. So this is the full buoyancy. This is the undilute instability term, which is the near surface air that is rising, but it's still not entraining the drier air around, so it's undilute. Dilute plume usually means the buoyancy is so strong and rising so strong that there is entrainment of drier air which dilutes the plume, and this is the moisture term. So the BL is split into the undilute instability term and the moisture term. And here again you are looking at ENSO risk ratio, remember how it's defined, and the buoyancy, and you see the same picture for full buoyancy, undilute instability term, and moisture term. So let's read a bit. Pearson correlation coefficient of Nino 3.4 versus 99th percentile daily values of the full buoyancy metric, just the undilute instability term, and just the moisture term for JJS. The black contours enclose areas deemed statistically significant on the basis of a false discovery rate of 0.3. So there are some statistical details. Regional ENSO risk ratios of regional ENSO risk ratios of rainy day buoyancy for the full metric, just the undilute and the moisture terms respectively. Thick lines denote where the risk ratio is significantly different from unity on the basis of a permutation test. Overlaid vertical lines denote the climatological 99th percentile value of each region of the given buoyancy component. So basically you have to make sure that you are statistically significantly different during ENSO years. What then accounts for these convective buoyancy signals? Preliminary results point toward synoptic low pressure systems which generate heavy rainfall within their course and track predominantly over central India, although occasionally traveling further south and extending to Rajasthan in the northwest. A prior study indicates that course of monsoon low pressure systems are very humid and that during El Nino summers the rainfall within these cores is enhanced. Okay. One possibility is that those low pressure systems tracks over one possibility is that those low pressure system tracks over and ending in India are favored by El Nino at the expense of those over peninsular India and any long tracks that might reach northwestern India. This would promote very humid, buoyant days and with them extreme rainfall likelihoods in central eastern India and suppress them in southeast and northwest. So they are getting a bit speculative here because they haven't resolved those kind of details in this paper, which I'm sure somebody else will do it or they will follow up soon. What is the outlook then? Seasonal forecasts, climate change and other extensions are possible despite ENSO's known spring predictability barrier. Existing seasonal forecasts of ENSO during boreal summer are skillful. For example, the multi-model mean forecasted JJS value of Nino 3.4 from the North American multi-model ensemble seasonal forecast integrations initialized annually on May 1st are correlated with the actual value at 0.86 over 1981 to 2020. That's a very high skill. Spring predictability barrier basically says that if you initialize the El Nino forecast during March, April, May, it tends to fail because there is a predictability barrier, and then there are a lot of papers saying actually there is no such barrier. This is what this is implying here, that there is skill even when you initialize on May 1st. Doesn't say what happened if you initialize in March or April, but nonetheless, we have recomputed the correlations between the JJS cutoff rain rate and Nino 3.4 using this forecasted value, and the overall signals remain. This raises the prospect of skillful ENSO-based seasonal forecasts of extreme rainfall probabilities within monsoonal India. However, the statistical significance weakens non-trivially, and risk ratios that use NMME first May forecasted JJS Nino 3.4 show considerably weaker separation between El Nino and La Nina summers in terms of the distribution of extremes or the statistics of extremes. Providing societally actionable information may therefore require even more skillful forecasts of the state of the ENSO. The strength of the ENSO and the diversity or the exact pattern of the ENSO may affect these results. By using more than a century-long data, they haven't separated the dependence of this result of enhanced extremes by El Nino compared to La Nina by the duration, intensity, etc. of the El Niños. Obviously, those may matter. And just trying one model is never a good enough idea. Our approach could also be applied to climate variability modes in the Indian Ocean and Atlantic Oceans, thought to influence the summer monsoon as well as hourly rainfall. Many Indian summer monsoon rain events are considerably shorter than 24 hours in duration, and a study using hourly rainfall suggests that the average rain rate during rainy hours increases with El Nino over much of the tropics. Perhaps, as for daily rain in the Indian summer monsoon, these signals reflect buoyancy-driven increased extremes. Okay, so the very nice study kind of adds some details that haven't been carefully considered, but nonetheless, I thought I'll put it into record and let you see it. See you in the next topic.